All right, let's go ahead and let's get started, folks. I noticed that yesterday, quite a few of you had issues with uploading the material up to Classroom. Please make sure you look at Google Classroom today, and I've suggested an alternative way that you can try to get the material onto Classroom, uploaded on the Classroom. I hope that'll be sufficient. It'll hopefully work. If not, again, just let me know and we'll figure it out. Okay. Also, yesterday it seemed like the video was a little bit longer. What I'm going to try to do is I'm going to try to trim 5 minutes off of the video today and see if that leaves you enough time to get the work done and also submit by the end of the period. And so we'll see how that works. Like I said, we're going to have to tinker as we go through this. And I think maybe trimming 5 minutes off of the video lecture will help you then finish the work done in lecture during and the practice problem I give you at the end and submit everything by the end of the period. Okay, so let's see how that works out, and I hope it'll suffice. It'll be sufficient for us to get through the class. Okay. All right, so let's go ahead. Let's review where we left off with yesterday. We were talking about the Born-Haber cycle, and we were talking about how we can use that to calculate the different energies of involved in the formation of ionic compound. Remember, the ionic compound. The reason why it's stable, and we'll talk about this a little bit more in just a moment, because you have you have a lot of these ions, cations and anions that are interacting with each other in a very close and small space. It's that structure, that solid structure, that ionic lattice that allows us then to see them why ionic compounds are so stable. We know that they're stable because they have very high melting points and very high boiling points. Okay, so with that said, then we saw then in this in the last couple of lectures here that the lattice energy usually accounts for that. That's the energy that is given off when two ions in the gaseous state come together, and when they come together with other ions to form this crystal lattice, the stability arises from there. Okay. All right. So with that said, then I also mentioned that the lattice energy is an energy that's very difficult for us to measure. We can't actually measure that particular energy. And so with that said, then we use other energies that we can measure. For example, the ionization energy, electron affinity, we can measure those and then use a process that's similar to what we saw with Tesla's law when we dealt with energies in order then to calculate for the that lattice energy itself. Okay, we were able to calculate for that energy using a version of Coulomb's law, and we were able to do that as well. We use that to do a quick qualitative analysis of the bond strengths of different ionic compounds, and that was a problem that we started out with yesterday. Okay. All right, so we left off, and I asked you to do this here. We left off at number 61. This is a problem from your homework. It's on page 407. I asked you to finish this problem here, and what I'd like to do is go ahead and finish it with you today, and then we'll continue on. Okay. All right, so we were asked in this particular problem here to find the energy of sublimation, okay, and the energy of sublimation. So let's go ahead and start with this one. This is the equation that we were dealing with. Okay, so that's the reaction we are looking at, the formation of lithium iodide. This is the enthalpy of formation. That's the delta H formation for this reaction here. So to use the Born-Haber cycle, I would suggest that you just write it out the way we did when we were calculating for the enthalpy of reaction here. So the very first step then, remember, is going to be the lithium becoming solid. So the lithium metal becoming a gas, and that's your energy of enthalpy. Okay, so that's what we were solving for here. That's the delta H of sublimation. Sorry. Okay, so that's what we were looking for right there. Okay, that's the very first step. Then remember, the second step is we're going to take the lithium in the gaseous state. We're going to ionize it to the lithium ion, and that's going to be your enthalpy of the ionization energy. Let's go write that down. And we were given that ionization energy here as 520, positive 520 kilojoules per mole. Okay. After that, then we have to break up the iodine molecule into the separate iodine atoms, and that's the energy of dissociation. So that's the bond energy here. So we'll write that down. It's a delta H of bond energy, and that was a positive 151 kilojoules per mole. Understand, we're only taking half of that bond energy. The bond energy is the energy that holds the two atoms together. So we're going to take half of that, because we only have a half here. We're going to take half of that, and so we're going to take half the bond energy. And then the next step then is we need to ionize the iodine atom, which means that it has to pick up an electron. Okay, and so this is going to be the electron affinity energy, the electron affinity, which is what we have right here. Right here. Okay, so that's electron affinity for iodine, and that's going to be a minus 295 kilojoules per mole. Okay, and then finally the lattice energy, which brings together then the lithium ion in the gaseous state with the iodide ion in the gaseous state to give us the lithium iodide solid. Okay, and then therefore we have the lattice energy, and that was given to us right here as minus negative 753 kilojoules per mole. Okay. All right, so what we did then was we added all this up, and if we add that up, we'll get this equation here of lithium as a solid plus 1/2 iodine molecule as a gas, sorry. Okay, and then we'll get the lithium iodide solid here. And what we did here is we added all that up to get the delta H standard of formation, and that was minus 292 kilojoules per mole. Okay. All right, so that's not what we want. We want to be able to get this value here. Okay, so we want to obtain that value. So hopefully you recognize then that what we're going to do here is we're going to add whatever we have here. We're going to sum this up here and subtract it from this value for the enthalpy of formation. So I'm going to go ahead and erase this really quickly, and let me see, go down to slide. Okay. And so what we see here then, and we're going to solve for this one. We're going to solve then for the delta H of sublimation. In order to do that, then we're going to take the delta H standard of formation. We're going to subtract from that then all the other energies, the ionization energy plus the electron affinity plus the bond energy plus the lattice energy. So we're going to add all those up and then subtract it from the enthalpy of formation here. Okay, so that's going to be minus 292 kilojoules per mole. Okay, we're going to subtract from that ionization energy, which is going to be 520, positive 520 kilojoules per mole. Okay, we're going to add to that the bond energy, which is 1/2, 151 kilojoules per mole. Okay, and to that we're going to add the bond energy, which is negative 295 kilojoules per mole. Sorry, I'm running out of room here. And to that we're going to add the lattice energy, which was negative 753 kilojoules per mole. Okay, and so you add all that up, then you're going to get a value that is positive 161 kilojoules per mole, and that, folks, is your energy of sublimation to sublimate the solid lithium to gaseous lithium. Okay, so that's the Born-Haber cycle, folks. I think it's pretty straightforward. Not that difficult. I think you'll please practice it. I didn't see anyone come by yesterday after school, so please come on by after school to Zoom classroom and get that extra tutorial if you need it. And then we'll go over these problems if you have to. Okay. All right. Well, that's it for the main calculation of the lattice energy. Like I said, I think it's a pretty straightforward calculation. Not that difficult. So what I'd like to do then is I want to continue on. Make sure you understand then that when we talk about ionic bonds, okay, you have to understand then that no single bond between two atoms is going to be completely ionic in nature. Okay, so, and again, what I want to make clear to you then is that we're discussing then the bond between two atoms. Okay, and so we will never see two atoms reach 100% ionic character. That just doesn't really quite happen. There's still going to be a back and forth. There's going to be an electron, the electron, or meaning that an electron is never fully transferred from one atom to another. That remember, when the interaction occurs, based upon what we learned with quantum mechanics, we really don't know what the electrons are doing, where they are. So there's a possibility that even in an ionic bond, the electrons move back and forth. Okay? And so make sure you understand then that we can calculate, make sure you understand that we will never get 100% ionic character for any bond between two particular atoms. And this is going to be key here, folks. And I want to point out here, this is the atoms in the gaseous state. Now understand, when we talk about the interaction in the solid state, what we're pointing out then is that this is the interaction between positive and negative atoms in a lattice. Okay, so you have a whole lot of atoms interacting with one another, which is going to be the key difference between what we're going to talk about with discrete pairs, what happens when the in the solid state. Okay, so in the solid state, then we have multiple ions interacting with one another, and that's why it the ionic compound in the solid state has a much more the interaction is much stronger. Okay. Now understand that in the gaseous state here, the reason why we don't have that strong of interaction is just these gaseous ions are so far apart from one another. But when we talk about the ionic character of an ionic bond, we were discussing then the character of discrete pairs. Okay. All right. So with that said, then we can calculate for the percent ionic character, and that's pretty straightforward. Then we're going to calculate for the measured dipole, versus the calculated dipole times 100. We get these numbers here. We can find then the percent ionic character of a particular atom. And if we graph it here, you're going to notice then that, yeah, the more electronegative the atoms are, the more the difference in their electronegativity, the greater that difference is, the more ionic character we have here. But if you notice, there is no compound here that fully reaches 100%. So even though all of these compounds here highlighted in pink are ionic compounds, metal versus the non-metal, these will never completely be 100% ionic in character. Okay, but however, like I said, as the difference increases, we do see then that the percent ionic character also increases as well. And now, mind you, again, what we're dealing with here is the individual bonds, the bond between the two individual atoms, rather than in a solid structure. Okay, so make sure you keep that in mind as we go forward with this. Okay, all right. So that's the case then with ionic bonds. Okay, so that pretty much allows us then to finish up our discussion by summarizing then that the way that we're going to define an ionic bond versus a covalent bond versus a polar covalent bond is that when an ionic compound melts, and when you melt it, it will conduct an electrical current. The conduction of an electrical current is what's going to be the defining feature of an ionic bond versus an ionic compound versus a polar compound itself. Okay, so that's what we're going to use then to distinguish between ionic bonds versus covalent bonds. Okay. All right. So with that said, then we are done with ionic bonding. Okay. So what we're going to do moving forward here is we're going to be focusing our attention on the covalent interaction. That is the sharing of electrons between two bonds, between two atoms. Okay. So with covalent bonds, then you see many of these. Okay, there's many of these that appear in our what we experience. Most of what we have then are most of the compounds that we come across are covalently bound together. Okay. What we're going to do then is we were able to examine the bond energies involved in ionic bonds. What we're going to do moving forward then is we're going to focus on the bond energies for covalent bonds. And I'm sorry. Okay. All right. So with the bond energies here, and I'm sorry, two previous slides I skipped over quickly. It's just talking about how the models that we use to describe the bond energies, the bonds between ionic bonds and covalent bonds. These are just our way of explaining them. Again, you know, as science progresses, those models have to change. Okay. All right. So with that said, then we're going to take a look at the bond energies that occur. We're going to be able to calculate for them and then and determine the bond energies between two non-metal atoms. So we want to find then the bond energies of the covalent bonds. Okay. And so keep this in mind, and this is going to be something that you'll need to remember. Okay, when bonds break, when we break covalent bonds, when covalent bonds break, when we break them, okay, energy has to be added. Okay, which means then that energy, the enthalpy for that reaction is going to be positive. We already saw that. Okay, when bonds form, when you form bonds, energy is going to be released, which means then delta H is going to be negative for that particular process. Okay, so what we do is this bond energy here, that what we describe then, what we'll describe then is the bond energy as we move forward then is going to be dependent on the environment that that particular bond is in. So what we're going to do is let's examine then the carbon-hydrogen bond, the CH bond in a molecule of methane here. And based on that, you can see then that the energy involved in forming or breaking these single bonds here, okay, will depend on what is left over. That is what we refer to as the environment, the molecular environment for that particular bond. Okay? So this table here points out for us the bond energy required to break each one of those carbon-hydrogen bonds successfully. Okay, so for the very first one here, we're breaking one carbon-hydrogen bond, so we're left with CH3 and the hydrogen atom by itself. And the energy required to do that then is going to be 435, positive 435 kilojoules per mole. Okay, and if you notice, then that's not the same. That's not the same for each one of these. So each one of these here describes then the energy needed to break successive carbon-hydrogen bonds, and the bond energies are not the same. What this tells us then is that as we break each one of these bonds, what's left over then changes the environment of the molecule, changes the environment of this interaction here. And so with that said, then it alters the amount of energy needed to break these bonds here. And that's what we mean then by describing the bond energy as being dependent on the environment in which these bonds are found in. Okay, all right. So how do we go about doing this? How do we go about calculating? Because you will see values for the bond energy. Well, essentially what we do then is we're going to take the average. And this is not quite accurate here, because if you notice the average of all those bond energies doesn't match any of these here. But that's the best that we can do. What we're going to do then is we describe then the average. And if you take a look at these tables here, this table here, all of these bond energies are basically averages. They are average bond energies for each one of these particular bonds. But we're going to use these here. Okay, and you've seen these bond energies before. You've seen this table before. We talked about the energy needed to break these bonds here. Okay, so again, these bond energies then are basically averages, okay, of each one of these different types of bonds here. Okay, all right. We also talked about the relationship between bond length and bond energy. We saw then that the bond length is the distance between these two atoms. That changes as you change the type of bond here, as well as the bond energy. So if you take a look at the carbon interaction here, single bond versus double versus triple, the bond length is going to decrease as you increase more bonds. So as you have more interactions between these atoms here, the bond length decreases, but the bond energy increases. Okay, so make sure you keep that in mind, which kind of makes sense. If you have more bonds holding atoms together, you expect then that should be stronger. Okay? So what can we do with these bond energies here? What's the purpose of introducing these bond energies? Well, what we can do with these bond energies is that we can use the bond energies here to calculate for the energies involved in a reaction involving covalent molecules, molecular compounds. Okay, and this process is even easier than what we had to do with the ionic compounds. So essentially what we're going to do then is we're going to define the energy of formation, or define the energy involved in a particular chemical reaction involving covalent compounds, molecular compounds. We just have to find then and sum up and sum up all of the bonds that are broken and all of the bonds that will form. So this would be the reactants then, folks. Make sure you understand that this will be all of the reactants, because reactants have to break their interactions. Okay, so this will be all the bond energies for the reactants. This will be all the bond energies for the products, because those have to form for product to form. So we're going to use the bond energies. We're going to sum them up, and we can get then the energy involved in that particular reaction. We can find the energy that's either going to be given off or absorbed by a particular reaction. And that's why we want to be able to use, and that's why I want to introduce these bond energies to you. understand this calculation here does not apply to ionic compounds. We don't do this with ionic compounds. This is for reactions that involve molecular compounds. And so I'm running low on time here. And so what I'd like to do is work out one problem for you. Okay, let's work out this problem together. Okay, and then I'm going to ask you to do one problem so you can get practice with this. Okay, so here's the reaction. Okay, this is the reaction to form hydrogen fluoride. So we have hydrogen reacting with fluorine. I'll give you the values in just a moment, but if you look on page 374, table 8.4, it gives you the bond energies. Okay, and so we want to find here then the enthalpy, the energy either released or absorbed in this process here. Okay, so what do we do? Well, let's go ahead and write this down. So if you have the table in front of you, good. If not, then I'll write it down here for you. In that table, then we're told that the bond energy for the average bond energy for this bond right here, which we have to break. This bond has to break in order for this to form here. That's going to be 432 kilojoules per mole. Okay. For the fluorine atom molecule, okay, the bond energy involved is this. And if you notice, this is all the bond energies are assuming bond breaking here. Okay, so these will all be positive. The amount of energy needed to break the fluorine-fluorine bond is 154 kilojoules per mole. Okay, all right. And then the bond energy for the hydrogen-fluorine bond here, again, all these bond energies are assuming bonds being broken, because all these are positive. Okay, so 565 kilojoules per mole. Okay, so those are the values from your book. Now, let's go ahead and let's plug it into the equation that we had. So to find then the energy associated with this reaction, then we want to sum up all the bond energies. And remember, we've used bond energies when we calculated for the lattice energies. Bond energies, the energy needed to break the bonds. Okay. Okay, so this bond energy here is going to be for the reactants. Okay, and from that we're going to subtract all the bond energies. So the Greek letter sigma here, capital Greek letter sigma, means the sum. The bond energies for the product. Okay, this negative sign right here will make all these bonds here, all these energies here negative. So don't put in the negative sign here. Okay, so let's go ahead and plug in our values. Okay, so then to start out with, then the bond energies for hydrogen. So this is going to be positive 432 kilojoules per mole. To that, we're going to add a positive value of 154 kilojoules per mole. Okay, so that represents then all the energies needed to break these two bonds here. Okay. Then we're going to sum up the bond energies for the what forms it, hydrogen fluoride. Okay, so we have then 565, sorry. Let me go ahead and write that down. Okay, so 565 kilojoules per mole. But if you notice here, we don't have just 1 mole of hydrogen fluoride, we have 2 moles of hydrogen fluoride, so we have to double this right there. Okay, all right, so that's why the units here are going to be important as well. So that's it, folks. So the math, and if you do the math, you end up with an answer that is negative 544 kilojoules per mole. Okay, and so make sure you understand what this number means right here. This number means then that for this particular reaction, okay, which has an energy of that's associated with the negative 544 kilojoules per mole. Okay, that means then when this reaction runs, it actually gives off energy. At the end of this process, this is going to be an exothermic reaction. The negative sign means that this is going to be an exothermic reaction. Okay, so as an exothermic reaction, when this reaction runs, it's going to give off energy. And when you mix, that means then when you mix hydrogen and fluorine together, you're going to feel some heat being given off when that reaction runs. And that's what the negative sign there tells us. Okay. All right. What I'd like you to do then is, and again, I won't assign any problems from your textbook, but I would like you to work out number 6 here from your problem set, and work it out the best you can. Use the previous slide to help you. Rewind this video and help you with it. Work this problem out here, and we will start with this problem tomorrow. Okay, so please make sure you get that done. All right. I hope you folks have a good day. And again, if you have any questions, come by this afternoon to our Zoom classroom and get that extra tutorial. Okay, I'll see you folks tomorrow.